The production of specialty steels involves a highly controlled and sophisticated process designed to achieve superior mechanical, chemical, and physical properties. These steels are essential for critical applications in industries such as aerospace, automotive, energy, oil and gas, and precision engineering, where standard carbon steels do not meet performance requirements. The process begins with the melting of raw materials in an electric arc furnace, EAF, where scrap metal and carefully selected alloying elements such as chromium, nickel, molybdenum, vanadium, and manganese are combined to achieve specific properties such as strength, corrosion resistance, and heat resistance. Once melted, the steel undergoes secondary refining in a steel-making furnace, LF, where the steel's chemical composition is precisely adjusted and impurities are removed. For critical applications, vacuum degassing, VOD, is performed to remove dissolved gases such as oxygen, hydrogen, and nitrogen, ensuring a high level of cleanliness and homogeneity. After refining, the liquid steel is cast into the desired shapes, such as ingots, billets, or billets. These are then processed by hot forging or hot rolling to form semi-finished products such as bars, plates, or rods. Forging improves the internal grain structure and mechanical integrity, which is important for components subject to high stress or fatigue. The next stage is heat treatment, which includes processes such as quenching, tempering, annealing, or normalizing. These treatments enhance specific properties, such as hardness, toughness, and dimensional stability, depending on the intended use of the steel. Machining operations can then take place, and each batch undergoes rigorous quality control, including ultrasonic testing, tensile testing, hardness testing, metallographic testing, and chemical analysis to ensure compliance with international standards. Special steels are manufactured with great precision and expertise, delivering high performance, reliability, and durability in harsh environments. Their production requires not only advanced equipment, but also extensive knowledge of metallurgy and strict process discipline, making them the cornerstone of modern industrial innovation. This method eliminates combustion-related emissions and reduces scale formation, improving surface quality and minimizing material waste. The inductive forge system stands out for its modular design, which allows users to tailor the heater to match specific production needs, whether for small-scale batch production or high-throughput operations. The tractor feed system is a key feature, automating billet loading and transport through the induction coil. It offers accurate, repeatable billet positioning and smooth feeding at variable speeds. This enhances process control, reduces operator intervention, and ensures consistent heating along the billet's length. It also minimizes downtime by allowing easy adjustment and maintenance access. With advanced diagnostics and user-friendly controls, operators can monitor temperature, power levels, and system performance in real time. Optional features include pyrometers for temperature feedback and integration with press automation. Mannstat specializes in the production of high-quality metal components for a wide range of industries, including automotive, construction, material handling, and more. Their manufacturing process begins with the raw material supply via conveyor belt, which ensures smooth and efficient processing of materials from the very beginning, allowing for maximum productivity and consistency. In the lighter material range, the company focuses on the heating and warm forming of metals, ensuring that each product meets the highest standards of quality and precision. They use state-of-the-art technology to perform continuous contour checks, utilizing laser triangulation to guarantee accurate shaping and precise dimensional consistency. This product range spans from 2 to 35 kilograms per meter and serves industries such as automotive, construction, and beyond. Precision is essential in these sectors, and Mannstat's advanced methods ensure that the final products meet these stringent demands. To further enhance production efficiency, Mannstat employs FEM, finite element method simulations. This allows the company to optimize the manufacturing process, reducing waste and improving product consistency. Additionally, Mannstat manufactures its own specialized tools, ensuring the highest level of control over every step of the process and product quality. In the heavier material range, Mannstat handles raw materials from 15 to 180 kilograms per meter, catering to industries like material handling, commercial vehicles, and heavy machinery. The manufacturing processes for these materials involve similar heating and warm forming procedures, supplemented by inline contour measurement and surface inspection while the materials are still hot. Laser triangulation technology is used for precise torsion and straightness checks, ensuring the highest quality. Mannstat also offers a robot stacking system for customized packaging with lengths up to 24 meters. The company provides tailored logistics concepts and has the capacity for worldwide shipping, ensuring that their products are efficiently delivered to customers across the globe. The production and testing process of Andritz pumps begins with design and development, where experienced engineers create pump models with in-depth knowledge of the entire process, from design to installation. Customer requirements and needs are carefully considered to ensure the best possible product. The pump components are precisely machined using CNC milling, ensuring high accuracy. Thermal treatment improves the material's mechanical properties, ensuring durability and wear resistance. Once production is complete, the pumps undergo testing at the test stands in Astro, Graz, Austria, where performance, durability, and operational stability are thoroughly evaluated. Andritz pumps achieve up to 92% efficiency in split-case pumps, helping to save energy and optimize operational efficiency. Additionally, the company offers custom-designed pumps to meet specific customer needs, including multi-stage submersible pumps with high wear resistance and exceptional reliability. Each product is certified according to international quality standards such as ISO 9001, ISO 14001, and KTA, ensuring reliability and optimal performance. With this rigorous process, the company guarantees that its pumps deliver high performance, reliability, and longevity, meeting the demanding requirements of various industries worldwide.
Casting is a thorough and multi-stage process that transforms raw materials into finished products ready for use. In this video, we delve deep into the various stages involved in the casting work at our sand foundry, showcasing the entire journey from the preparation of molds to the final delivery of the finished product to the customer. The process begins with mold preparation, where the team ensures that the mold is perfectly crafted to meet the specific needs of the product. This involves making sure that the mold's dimensions are precise, and the material used is of high quality to ensure durability and strength in the final cast. Next, the mold undergoes painting, a critical step that prepares the surface for the casting process. The coating ensures that the mold remains smooth and that the final product does not have any imperfections caused by the mold's surface texture. Following this, the yelling of the mold takes place. This step involves creating a consistent and even thickness across the mold to ensure that the casting process goes smoothly. The material inside the mold must be perfectly distributed to avoid any weak spots in the final product. The next step is the sealing of the mold. This is an essential process where any potential gaps or spaces are sealed off to ensure that no metal escapes during the casting process, preventing any defects or loss of material. The next stage involves metal control and analysis. Before the molten metal is poured into the mold, it is carefully analyzed and tested for impurities, composition, and temperature to ensure it meets the required standards. The team checks for things like chemical composition, melting point, and any other factors that could affect the quality of the final product. Once everything is properly prepared, the process moves to casting. The molten metal is poured into the sealed mold, where it cools and solidifies into the shape of the intended product. This step requires extreme precision, as even slight variations in temperature or pouring speed can lead to defects in the casting. After the metal has solidified, the cast product is removed from the mold in the unmolding stage. This is done with care, as the product is fragile during this stage and can be easily damaged. The piece is then cleaned and inspected to ensure that all of the required specifications are met. If any imperfections are detected, the piece is returned to the furnace for reprocessing. The next stage in the process is fettling. Here, any remaining imperfections or excess material from the casting process is removed. This is done using a combination of tools and machinery to smooth out the surface and ensure that the final piece meets the required shape and dimensions. After fettling, the casting is further refined through grinding and polishing. The goal of this stage is to enhance the surface finish of the product, removing any rough edges or marks left from the casting process. The smooth surface is critical for both aesthetic and functional purposes, especially for parts that will be used in precision applications. Once the product is thoroughly cleaned and polished, it undergoes a series of non-destructive testing. This includes techniques such as ultrasonic testing and X-ray inspections, which help detect any internal defects that might not be visible on the surface. These tests ensure that the integrity of the casting is intact and that it meets the required strength standards. In some cases, additional heat treatment is applied to the cast product. This process involves heating the casting to a specific temperature and then cooling it rapidly to alter the material's properties. This enhances the strength and durability of the product, making it suitable for high-performance applications. Once heat treatment is completed, the casting is once again inspected for any signs of deformation or stress. Any minor issues are corrected during this stage to ensure that the product meets the rigorous standards set by the foundry. With the final checks complete, the cast product is ready for assembly, if required. The assembly process is handled with great attention to detail, ensuring that all parts are properly fitted and secured. At this point, the product is ready for the final inspection before it is released. Shaping metal through rotation may seem simple, but the process behind it is precise and physically demanding. This is metal spinning, the transformation of flat metal discs into complex, symmetrical parts like nose cones, wind vanes, or satellite components. The process begins with a flat aluminum blank, clamped securely against a shaped mandrel on a spinning lathe. The mandrel defines the final shape of the part. As the lathe spins at high speed, a skilled operator applies force using hand tools or automated rollers to gradually form the metal over the mandrel. The key lies in controlling heat, pressure, and motion. No heat is applied initially, but as the metal is deformed, friction and pressure raise the temperature, making the material more ductile. In some cases, torches or induction heaters are used to soften thicker metals. During spinning, the operator maintains consistent tool pressure to avoid wrinkling or tearing, while carefully guiding the tool to follow the shape of the mandrel. This results in seamless, aerodynamic forms that would be difficult or expensive to produce by other methods. In this demonstration, the part being formed is a nose cone for a wind vane. The cone starts as a flat disc and is shaped entirely by manual spinning. Once the rough shape is complete, the operator finishes the form by smoothing the surface and trimming excess material. The process requires both strength and intuition. Each adjustment must respond to subtle changes in resistance and form. Depending on the material, several passes may be necessary, gradually working the metal into its final contour. Any inconsistency in speed or tool pressure can leave imperfections, making operator experience critical. What makes metal spinning unique is its flexibility. It can accommodate one-off custom parts or low-volume production runs with minimal tooling. Unlike deep drawing or stamping, it doesn't require expensive dies, and adjustments can be made quickly by modifying the mandrel or tooling path. It's ideal for aerospace, energy, and scientific industries, where both performance and precision matter. Metal spinning is as much art as it is engineering. Each part reflects the operator's skill, material behavior, and dynamic forces at play. With the right balance of speed, pressure, and finesse, flat metal becomes functional form, seamless, strong, and efficient. Precision meets versatility in the world of advanced machining. The Gemini's GM series multi-process lathes exemplify this synergy, integrating turning, milling, drilling, and grinding into a single, robust platform. This consolidation streamlines production, minimizes setup times, and enhances accuracy across complex manufacturing tasks. At the heart of these machines lies a modular design, allowing for customization to meet diverse industrial needs. With features like automatic head and tool changers, high dynamic slides, and a powerful C-axis, the GM series ensures seamless transitions between operations. This adaptability is crucial for industries requiring precision and efficiency. The GM9 model, for instance, boasts a turnable swing of up to 2,500 millimeters and accommodates workpieces weighing between 25 to 80 tons. Its advanced capabilities make it ideal for sectors like energy, railways, and heavy machinery manufacturing. The integration of Industry 4.0 solutions further enhances its performance, offering real-time monitoring and improved process control. Each machine is configured according to the specific geometry, material, and tolerance needs of the part being produced. Multitasking capabilities reduce the need to transfer components between machines, minimizing handling risks and geometric errors. This approach not only improves productivity, but also ensures tighter compliance with quality standards. Advanced control software provides intuitive interfaces for programming and monitoring, helping operators maintain consistent part quality. High-performance spindles deliver stable torque across a wide range of speeds, enabling efficient machining of both light and heavy-duty materials. Optional attachments like steady rests, angle heads, and boring bars extend the machine's capabilities without redesigning workflows. Scalability is another key advantage. These machines can be adapted over time to match evolving production requirements. The result is a reduced total cost of ownership through increased uptime, fewer work-holding devices, and consolidated processes. This intelligent design philosophy reflects a broader shift towards smart, resource-efficient manufacturing. Ergonomics and safety are also paramount. Design elements such as low bed height, walkable platforms, and enhanced lighting ensure operator comfort and security. Maintenance is simplified through features like centralized lubrication systems and easy access panels, reducing downtime and operational costs. Incorporating eco-design principles, these lathes aim to reduce environmental impact. Measures include energy-efficient components, optimized material usage, and improved waste management systems. This commitment to sustainability aligns with modern manufacturing's evolving standards. In summary, the Gemini's GM series represents a fusion of innovation, efficiency, and adaptability. By consolidating multiple machining processes into one platform, it addresses the complex demands of contemporary manufacturing, setting a new benchmark in the industry. Drilling deep holes in large steel components presents serious challenges, especially when precision and tool stability are critical. At voestalpine Foundry in Linz, 4 220 mm diameter holes, each 1,500 mm deep, had to be created in a 26-ton quenched and tempered steel housing. This task was made possible by a specialized tool concept from Hermann Bilz. The custom tool features an HSS centering drill with internal cooling, 6 inner HSS indexable inserts, and 6 outer carbide inserts, optimized for the increasing cutting speed from center to edge. Rather than using a modular system, this solution was designed as a single integrated tool with an SK60 interface, coolant adaptation, and a 125 mm diameter holder. The first half of each bore is drilled from one side, reaching 750 mm. The workpiece is then rotated 180 degrees, and the process is repeated from the opposite side, stopping just before breakthrough. Switching to a full HSS configuration and reducing cutting speed allows the tool to engage more aggressively. Feed is increased toward the end, ensuring a smooth, stable breakthrough without tool deflection. In heavy fabrication, forming massive steel blanks into precisely curved heads is no small feat. The PAO 1000X9100 dishing press tackles this with power and control, handling cold blanks up to 9,100 mm in diameter and 90 mm thick, within a lifting limit of 27 tons. Backed by a 1,000-ton capacity and a CNC-controlled manipulator, this system shapes steel with unmatched repeatability and surface quality. Each axis is monitored and adjusted proportionally, maintaining calibration through constant feedback on pressure and position. The manipulator rotates, lifts, and positions the blank with minimal manual input, accelerating production while ensuring consistent curvature. The multi-stack dishing configuration allows multiple forming sequences without repositioning, effectively cutting down process time. Built for performance, the system operates with fast downstroke, compression, and return speeds, key to high-volume output. With over 30 years of development, the automation ensures uninterrupted, identical forming cycles. From heads for pressure vessels to large tank components, this setup meets industrial demands for speed, scale, and accuracy. Casting large, complex engine parts requires a precise balance of temperature, timing, and technique. At this foundry, over a century of experience in marine diesel engine manufacturing shapes every step of the process. It begins with mold preparation. Resin-bonded sand mixed with a hardening agent is used to form strong, heat-resistant molds. After shaping, core parts are inserted, and an alcohol-based coating is applied to the interior surfaces. This layer ensures smoother cast surfaces and reduces sand adhesion during pouring. Once assembled, the mold is closed and prepped for pouring. The molten metal is heated to 1,343 degrees Celsius, with a second phase reaching 1,363 degrees Celsius for different casting needs. Pouring is a coordinated task where timing and consistency determine casting integrity. Skilled workers guide the ladle to pour the molten metal evenly into the mold cavity, minimizing turbulence and reducing the risk of defects. Throughout the process, temperature monitoring systems ensure thermal stability. Each pour is documented and recorded to trace back any irregularities. Even minor temperature fluctuations can cause internal voids or dimensional inaccuracies. For large parts, multi-point thermocouples are often used. These provide real-time data across different mold sections. Such attention to detail is critical in marine-grade components where failure is not an option. After cooling and solidification, the mold is broken open and the casting removed. At this point, the rough cast part undergoes initial cleaning to remove excess material and sand. High-performance 3D scanners then inspect the geometry, comparing it to the original design with micron-level precision. Any unnecessary material or surface imperfections are trimmed or ground away by hand during the finishing phase. Surface refinement can also include localized machining when tight tolerances are required. In some cases, secondary heat treatment is applied to enhance mechanical properties. These steps contribute to greater reliability under load and prolonged service life in marine applications. The final inspection ensures that each component meets strict dimensional and surface requirements. This process supports the production of heavy-duty engine parts capable of withstanding extreme marine environments. While most of the work is hidden within engines, the casting quality here is critical to long-term performance and safety. By combining advanced tools like high-temperature pouring control and 3D scanning with traditional craftsmanship, this foundry maintains consistent quality across every part produced. These techniques, refined through a legacy of marine engine manufacturing, continue to support high-precision industries worldwide. High-speed billet cutting demands precision, durability, and clean results. In this setup, a Kinkhelder CX6 circular saw blade slices through a stainless steel billet in just 22 seconds. Mounted on the Mega CS150S saw, the system ensures reduced lead times, tight tolerances, extended blade life, and a remarkably smooth surface finish with every cut. Forging massive steel components begins with immense pressure. A moving overhead chain rotates the heavy ingot into position beneath the 10,000-ton press. Each press cycle reshapes the heated metal with force and precision. The process must be tightly controlled to ensure uniform grain flow throughout the part. At FAMA, an advanced XXL machining facility takes shape, featuring DMC 210U and DMC 340U centers with pallet systems and DMU 1000 SE twin-table portals. This installation enables efficient, large-scale, multi-process production with automation.
At the Euroblech Trade Fair in Hanover, Von Schauwen showcased an impressive exhibition of its metalworking production process, highlighting the precision and complexity of producing components through forging and machining. The manufacturing process consists of several critical steps that ensure high quality and accuracy for each part. The process begins with forging, where raw materials are heated and shaped by applying pressure to form the basic shape of the part. This step improves the mechanical properties of the material, making it stronger and more capable of withstanding heavy loads. After forging, the parts are saw-cut to the required dimensions, ensuring they are prepared for the next stages of machining. Saw cutting is essential for achieving accurate initial shapes before further refinement. Once the parts are cut, they undergo a quenching process, where the material is rapidly cooled to increase its hardness. This step enhances the part's strength and durability. The next step is tempering, a heat treatment that reduces the brittleness of the material and restores some ductility. After heat treatment, the parts undergo material testing to verify their mechanical properties. This testing includes both mechanical and chemical evaluations to ensure the material meets the necessary standards for performance and quality. The next phase involves pre-turning, where the parts are roughly machined to bring them closer to their final dimensions. After pre-turning, finished turning is performed using CNC machinery to achieve precise dimensions and high-quality surface finishes. This process ensures the part meets exact specifications for size and surface smoothness. Following turning, the parts undergo drilling, where holes or cavities are created according to the design requirements. Drilling is crucial for creating features such as bolt holes or openings necessary for the final assembly. An essential part of the process is non-destructive testing. NDT. This testing method, which includes ultrasonic, magnetic, or X-ray techniques, ensures the integrity of the parts without damaging them. NDT helps detect any hidden defects, ensuring that only high-quality products move forward in the production line. Once all processes are complete, the parts are carefully packed to protect them during transport. Packaging is designed to shield the components from external damage while in transit. Finally, the products are loaded and shipped to the customers or users. Throughout the entire manufacturing process, from forging to shipping, Von Schauen AG ensures that every component is produced with precision and meets the highest quality standards, demonstrating their commitment to technical excellence. The Hyundai WIAL 2100 Y-axis lathe is engineered to handle a wide range of workpieces, with a maximum turning diameter of 335 mm and a maximum turning length of 455 mm. These dimensions make it ideal for medium to large parts, offering the flexibility to handle various sizes and shapes. The lathe is equipped with an 8-inch main chuck, and a 6-inch sub-chuck, providing secure clamping and ensuring stable performance during high-speed operations. The sub-chuck is particularly beneficial for secondary operations, allowing the machine to perform more complex tasks without needing to reposition the workpiece. The spindle speeds of the Hyundai WIAL 2100 ensure efficient material removal and high-quality finishes. The main spindle operates at speeds of up to 4,500 revolutions per minute, suitable for general turning tasks, while the sub-spindle reaches speeds of up to 6,000 revolutions per minute, making it perfect for secondary operations that require finer finishes and higher speeds. These capabilities allow the machine to work with a wide range of materials, offering versatility for different manufacturing needs. In terms of feed travels, the lathe offers 210 mm in the X-axis, 100 mm in the Y-axis, with an optional 50 mm extension, and 580 mm in the Z-axis. The generous feed travels provide the machine with the flexibility to handle various geometries and part sizes, including off-center turning operations, which increases its versatility. The Y-axis movement is especially useful for off-center machining and complex part profiles, making the machine suitable for a wide range of precision tasks. The FANUC 321B controller, HW FANUC I-Series, provides reliable control for the Hyundai WIAL 2100. Known for its user-friendly interface and advanced capabilities, the FANUC controller ensures smooth operation and precise control over the machining process. This ensures high-quality results, minimal errors, and efficient machining with easy programming and setup. The Hyundai WIAL 2100Y axis lathe combines powerful performance, flexibility, and precision, making it an ideal choice for high-precision turning and machining tasks. Its advanced spindle speeds, generous feed travels, and reliable control system make it perfect for industries requiring accurate and efficient production, delivering high-quality results across a variety of applications. This machine is designed to improve productivity, reduce setup time, and enhance operational efficiency. The Huaqian M3 and M4 are advanced 5-axis machining centers engineered for high-precision applications in tool, die, and mold making, as well as heavy-duty cutting tasks. Both models exemplify Huaqian's commitment to stability, precision, and durability, featuring thermosymmetrical, FEM-optimized structures and in-house manufactured spindles. The M3 is equipped with a U700mm rotary table capable of supporting workpieces up to 800 kg. Its axis strokes are 750mm X, 900mm Y, and 550mm Z, facilitating the machining of complex geometries. The standard spindle operates at 20,000 revolutions per minute with 22 kilowatts power and 118 Nm torque, with optional configurations offering up to 24,000 revolutions per minute and 37 kilowatts. The machine's rapid traverse speeds reach up to 48 meters per minute, ensuring efficient operations. The BBT-40 tool shank and a tool magazine capacity of 40 tools, expandable to 60 or 90, further enhance its versatility. In contrast, the M4 is designed for larger and heavier workpieces, featuring a EU800 by 630 mm table with a load capacity of 1,200 kg. Its axis strokes are extended to 950 mm X, 1000 mm Y, and 650 mm Z, accommodating more substantial components. The standard spindle delivers 12,000 revolutions per minute, with 30 kilowatts power and 420 Nm torque, while an optional high-torque spindle offers 8,000 revolutions per minute, with 55 kilowatts power and 1,009 Nm torque. The M4 utilizes a BBT-50 tool shank and supports a tool magazine of 30 tools, expandable to 60. Both machines incorporate advanced features such as twin drives on the Y-axis, high-precision rotary encoders with 0.0001 degrees resolution, and actively cooled feed drives, ensuring consistent precision and performance. The M3 and M4 are available with various control systems, including FANUC 31i, Heidenhain TNC 640, and Sinumeric 1, providing flexibility to meet diverse operational requirements. The Index Mississippi 40C is a fully CNC-controlled multi-spindle automatic lathe designed for high-efficiency machining of bar and chuck parts. Its modular architecture allows for tailored configurations, featuring up to 12 CNC cross-slides, Y-axes, and synchronous spindles, enabling complete machining in a single setup. This versatility makes it suitable for both complex and simple components, enhancing productivity across various applications. Each spindle position in the Mississippi 40C is equipped with a V-shaped tool carrier arrangement, permitting both external and internal machining using either fixed or driven tools. This design ensures that the type of machining is determined solely by the tool holder, providing flexibility in operations. Additionally, the machine can be configured as a twin 3-spindle setup, allowing simultaneous machining of 2 workpieces, effectively doubling throughput. The Mississippi 40C boasts high dynamic performance, leveraging all the advantages of CNC technology. It supports complete machining with driven tools in all spindle positions, and features extremely fast, synchronous spindles with C-axis capabilities. For backworking operations, the machine accommodates up to 6 tools for one synchronous spindle, or a maximum of 12 tools when utilizing 2 synchronous spindles. This configuration enables complex rear-end machining without the need for additional setups. The spindle drum of the Mississippi 40C comprises 6 fluid-cooled motorized spindles, each offering infinitely variable speed control, high torque, and maintenance-free operation. This setup ensures optimal cutting conditions for each spindle position and tool, resulting in superior surface quality, reduced cycle times, and extended tool life. The machine's design also facilitates machining of high-strength materials that were previously challenging for multi-spindle machines. Equipped with advanced features such as high-precision rotary encoders with 0.0001 degrees resolution and actively cooled feed drives, the Mississippi 40C guarantees consistent precision and performance. Its compatibility with various control systems including FANUC 31i, Heidenhain TNC 640, and Sinumeric 1 offers flexibility to meet diverse operational requirements. Rottler Maschinenbau's SDM series heavy-duty lathes are engineered for precision machining of large-scale components such as rolls and turbine rotors. These machines accommodate workpieces up to approximately 20,000 millimeters in length and 2,500 millimeters in diameter, making them ideal for industries requiring the processing of substantial and heavy parts. The SDM series includes models like the SDM3, which supports turning diameters ranging from 2,000 to 2,500 millimeters and workpiece weights up to 50 tons. The production of artillery shell casings is a complex and highly automated process that combines heavy industrial machinery with advanced precision technology. This process ensures that each shell casing meets the highest standards for military and industrial use. Below is a comprehensive, step-by-step description of how special steel shell casings are manufactured using state-of-the-art equipment. The process begins with a magazine for automatic feeding of steel bars to the production line. These bars serve as the raw material for shell casings. Once positioned, the bars enter the BBS Brown-Boveri inductive heating system, which operates at a power of 1,450 kilowatts at a frequency of 500 Hz. This system uses electromagnetic induction to heat the bars rapidly and uniformly to forging temperatures, optimizing energy use and material consistency. Next, the heated bars are transferred to a FICEP hydraulic press shear, designed to cut steel bars with diameters of up to 130 millimeters. The machine shears the bars into billets with precise lengths required for the forging process. The billets are then directed to the Umuco hydraulic forging press, which includes 2 main units. The first unit is used for compression and push broaching, capable of exerting a pressing force of 630 tons and a drop hammer traverse of 1250 millimeter. This operation forms the billets into the rough shape of shell casings. The second unit is a drawing unit equipped with rolls and rings to calibrate the shell casing's dimensions. This section delivers a force of 200 tons and a drop hammer traverse of 3,200 millimeters, ensuring that the forged shells meet strict dimensional tolerances. Once forged, the hot shell casings are automatically arranged into pallets by a robotized stacker and sent for normalization, a heat treatment process that relieves internal stress and refines the grain structure of the steel, preparing it for precise machining. After normalization, the shell casings enter the mechanical processing line. The first stage involves a GF programmable hydrocopying lathe, which performs high-efficiency external turning of the shell casings. This is followed by final 130:1 programmable lathe, which handles the final internal turning to ensure tight tolerances and smooth internal surfaces critical for ballistic performance. For shell designs requiring curvature or contouring, the casings are passed to an automated technological module, ATM, used for bending operations. This system includes an automated billet charging magazine and an EMA Electro-Schulze inductive heating unit, which operates at 375 kilowatts and 1000 Hz to reheat the shells just prior to bending. Bending is carried out using the Usine de Wecker vibrating forging press, which applies vibrational energy to shape the shell casing gently and uniformly without introducing surface cracks or deformities. Throughout this stage, two manipulators support the movement and orientation of the shell casings, ensuring precise positioning at each step. Each stage of the production process is engineered for maximum efficiency, precision, and repeatability. From initial billet feeding to final machining and forming, the integration of automation and high-performance machinery ensures the reliable mass production of steel shell casings with consistent quality, ready for use in demanding military applications. The advanced technology also helps in minimizing waste, improving production speeds, and meeting strict international standards. The production process of a pump casing involves a series of precise and technically demanding steps to ensure the final product meets strict quality and performance standards. 3D model help determine the optimal shape, structure, and material suitable for the pump casing's intended application. Following this, a mold is created, typically from sand or metal, crafted with high accuracy to match the design specifications. The selected metal, usually gray cast iron or ductile iron, is then melted and poured into the mold. After cooling and solidification, the raw casting is removed and undergoes cleaning to eliminate sand residues and casting burrs. A heat treatment process follows to enhance the material's mechanical properties, increasing hardness and structural stability. The next stage is precision machining, using CNC lathes and milling machines to create exact surfaces, bolt holes, and mounting areas for seals and bearings. Once machining is complete, the casing is subjected to thorough quality inspections, including dimensional checks, ultrasonic testing, pressure leak tests, and surface finish evaluations. These ensure the product complies with industry standards and customer specifications. The final step involves applying anti-corrosion coatings and a protective paint finish to the pump casing. It is then carefully packed to prevent damage during transport. This entire process ensures that the pump casing is robust, reliable, and ready for use in various industrial pumping systems. Through stringent quality control at each stage, manufacturers can deliver pump casings with long service life, high performance, and minimal maintenance requirements, thereby meeting the demanding needs of industries such as water supply, wastewater treatment, and heavy machinery.
In this video, we observe the precise process of releasing a mooring buoy's anchor chain. The heavy chain, connected to a permanent anchor on the ocean floor, is carefully managed to ensure the buoy remains securely in place. This operation requires thorough coordination and specialized equipment to handle the substantial weight and tension involved. By controlling the chain's release, the team ensures the buoy's stability and readiness for vessels to moor safely. The entire procedure is executed under strict safety protocols to prevent accidents and ensure smooth deployment. Steel is everywhere, in cars, bridges, machines, even wind turbines. At Salzgitter Flakstahl, the journey from raw ore to finished steel begins with iron ore, sourced globally from regions like Scandinavia, Russia, Canada, and South America. These materials arrive by ship and rail and are processed in blast furnaces over 50 meters tall. By layering coke, ore, and limestone, and injecting air heated to 1,500 degrees Celsius, the furnace generates process gas that reaches up to 2,000 degrees Celsius to reduce and melt the ore. This yields up to 14,000 tons of pig iron daily. The molten iron flows into torpedo ladles and is then transferred to converters, where pure oxygen is injected to remove impurities. Scrap metal is added for cooling, stabilizing the converter temperature around 1,700 degrees Celsius. This blowing process transforms iron into crude steel, up to 12,500 tons per day. Next, alloying elements such as manganese, nickel, and chromium are added based on customer requirements. The steel is cast into slabs using continuous casting machines. These slabs, up to 35 centimeters thick and weighing up to 32 tons, are heated to 1,250 degrees Celsius and rolled into coils up to 2,000 meters long. The flexibility in alloying and shaping enables Salzgitter to meet a wide range of mechanical and structural specifications. Every stage of processing is tightly monitored to ensure quality and performance. Modern sensors and automated systems track temperatures, thicknesses, and surface conditions throughout the line. Some coils are cut into plates up to 16 millimeters thick for machinery and vehicle applications. Others are cold rolled to under 3 millimeters in thickness using 5-stand tandem mills, reaching speeds of 90 kilometers per hour. These coils undergo temper rolling for surface roughness, aiding in later processing like coating or painting. Further refinement includes electrolytic galvanizing, where zinc ions are deposited onto steel via an electric current, and hot dip galvanizing, where the steel is submerged in molten zinc at 450 degrees Celsius. Finally, organic coatings like paint or foil are applied as needed. With over 350 steel grades in storage, this facility supplies industries ranging from automotive to energy with tailor-made solutions. From high-pressure blades just 15 millimeters long to massive 4-meter turbine rotors, this plant engineers steam turbines up to 1,200 megawatts. Precision machining is handled by advanced robotic centers, including Georg, a 30-meter-long giant embedded in concrete, capable of replacing 3 machines at once. Every component reflects decades of R&D, modernization, and ecological focus.